All right, today we're going to look at rotation part 2 for our problem types. So our first problem type, this section, is first law with torques. So now we're going to be doing those equilibrium problems we did before, but now we're going to add in some torques. So how do you know it's first law problem? Because there's balanced torques, maybe it's constant omega, angular acceleration is 0, you see the word equilibrium, or the net torque is 0. As soon as you see one of those, the rest of them are true. So if you have a first law problem, you're going to draw a free body diagram with the locations of those forces. You're going to choose an axis to eliminate unknowns and sum up the torques that equal to 0, where clockwise is our negative direction, counterclockwise is our positive direction. Second law problems, this is kind of the inverse of this. So we have unbalanced torques, a changing omega, alpha is not 0 anymore, and we have a net torque. If that's the case, you're doing something very similar. You're drawing your free body diagram with locations. You just have to identify where is that axis of rotation for this one, because there is a definite one. You don't get to choose. And we sum up the torques and set it equal to I alpha. Again, same thing for clockwise being negative, counterclockwise being positive. We do introduce this moment of inertia. So moment of inertia is how easy or hard it is to cause something to change its rotation. So the moment of inertia, so if you're dealing with I, this is one way we can deal with it. So if you have an object going in a circle, okay, so if it is moving in a circle, we consider it a point mass. And so its moment of inertia is equal to mr squared, where r is the radius of that circle it's going in. If the object itself is actually rotating, then you're going to need to use your sheet that has our moments of inertia of different shapes on it. Okay. If you have multiple objects put together, okay, you can imagine like a wagon wheel with spokes, okay, and the wheel itself. What you do is you just find the moment of inertia of each of those parts and add it up to get the total moment of inertia. We can also do work kinetic energy now in rotation. You know you're going to be using work kinetic energy if it goes from one point to another. You're seeing things like heights and speeds, okay, and there's rotation or rolling. If that's true, you identify where your point 1, your point 2 is. You choose your height 0. You write out your work kinetic energy equation, start crossing stuff off. Now there is a little change here. When we talk about kinetic energy, there's going to be translational kinetic energy and rotational kinetic energy. So you cross things out as you have them, and if it is rolling, you do have this relationship between the omega here and the v here, that omega is equal to v divided by r. This can be done with multiple masses. I prefer to do multiple masses with forces and torques, but if you do want to do it, you just have to go through it and ask the question about each object and keep the parts that each object has, and you'll have an equation that might have 2 or 3 kinetic energies depending on how many objects you have. All right, conservation of angular momentum means there's no net torques, no external torques. You'll see words like freely rotating. If you have a single object, it's just going to be I omega, which is angular momentum, equals the final angular momentum. If you have multiple objects, maybe like 2 objects, you'll have the momentum before, which would be the sum of the 2 momentums, equals the sum afterwards. Be warned, though, when you do this one, that if things are rotating together, they are going to have a common omega, so you can factor that out. Now, for multiple masses, so if you have multiple masses that are connected, whether it's a wheel and then there's a string connected to a mass that's falling, if that is your situation, you're going to want to identify the acceleration, the linear quantities, and the angular acceleration as the positive direction. Okay? And you're going to be able to link those two in that alpha is equal to the linear acceleration divided by the connecting radius. The reason these two need to be positive is so that this equation works out. For anything that's linearly accelerating, you need to draw a free body diagram and generate a sum of the forces equals ma equation. Sum of the forces equals ma. And if it's rotationally accelerating, you need a torque free body diagram, and you're going to sum up the torques, set it equal to I alpha. If it's both angularly accelerating and linearly accelerating, you're going to have to do both of those equations for that object. And there will be a common force, and so the idea here is you're going to get a system of equations, and you're going to solve that system of equations.